In this video, we will learn about two other ways to represent a complex number by using the modulus and argument. For complex number z equals to x plus yi, the real and imaginary components can be read off the axis directly. If we focus on this right angle triangle made by z and the origin, the modulus r is the hypotenuse of the triangle, and the argument theta is the angle made between the hypotenuse and the base. Based on this triangle and our knowledge of trigonometry, we can say that the base of this triangle is r cosine theta and the height of this triangle is r sine theta. Since the base and the height of this triangle corresponds to x and y, we can thus say that x equals to r cosine theta and y equals to r sine theta. Therefore, the complex number z can be written as z equals to r cosine theta plus r sine theta times I. Or we can factorize the common factor r out to get the final form over here. This form is the trigonometric form or the polar form of a complex number. It is sometimes also called the modulus argument form of a complex number. In example 1, we need to express the complex numbers w and z in the polar form. So in order for us to do the conversion, we will need to first find out what are the modulus and the argument of these two complex numbers. So for the complex number w, the modulus will be 4 and the argument will be equals to negative 5 pi over 6. Therefore, we can say that the complex number w is equals to 4 multiplied by cosine negative 5 pi over 6 plus I sine negative 5 pi over 6. Also, we can make use of trigo properties to change this slightly into 4 cosine 5 pi over 6 minus I sine 5 pi over 6. Both of these forms are acceptable forms for the polar form when theta is a negative value. Next, we find out what is modulus of z. It will be equals to square root 2 and argument of z will be equals to negative pi over 4. Therefore, z will be equals to square root 2 cosine of negative pi over 4 plus I sine negative pi over 4, which we can also write as square root 2 cosine pi over 4 minus I sine pi over 4. Using the modulus and argument, we can also express a complex number in the Euler form. This form was discovered by Swiss mathematician Leonhard Euler, and it elegantly expresses the complex number in a very concise manner, as we shall see. How this formula comes about can be proven from the polar form which we have just learned. Z equals to r cosine theta plus I sine theta. We then apply the standard series expansion of cosine theta and sine theta to the polar form. And upon simplifying, we will get this expression over here. And if we compare this expression within the bracket with the expansion of e to the power of x, which is 1 plus x squared over 2 plus x cubed over 3 factorial, and so on, we can see that they are actually equivalent if we replace the x with I theta. Therefore, what this means is we can simplify this expression into e to the power of I theta, and therefore the complex number can be written in this form r e I theta, where r is the modulus of the complex number and theta is the argument of the complex number. The Euler form is very useful when it comes to multiplication, division, and application of powers between complex numbers, as we can make use of the indices properties with the Euler form. In contrast, for addition and subtraction, it will be easier to make use of the basic form x plus iy. In example 2, we need to express the complex numbers w and z in the Euler form. And to do so, we simply have to find out what are the modulus and argument of each of them. So for the complex number w, the modulus will be equals to 2 square root 2 and the argument of w will be equals to 3 pi over 4. Therefore, we can say that the complex number W is equals to R e I theta, and R will be 2 square root 2 e to the power of I 3 pi over 4. Likewise, for Z, its modulus will be equals to 2 and its argument will be equals to pi over 3. And therefore, the complex number Z can be written as 2 ei pi over 3. The Euler form is a very useful form, particularly if we know some identities associated with this form. Firstly, as with trigonometry, we know that arguments will repeat itself every 2 pi radians. Thus, e to the power of I theta is the same as e to the power of I theta plus 2k pi. Next, even purely real or purely imaginary numbers can be expressed in the Euler form. The real number 1 is equals to e to the power of I times 0. This can be easily seen from the Argand diagram, where the number 1 is going to lie on the positive real axis with a magnitude of 1. Therefore, 1 is equals to 1 ei, argument is going to be 0 because it's lying on the positive real axis, 0, which therefore gives us ei 0. Similarly, the imaginary number I, which has magnitude of 1, lies on the positive imaginary axis with an argument of pi over 2. Therefore, I can be written as 1 ei pi over 2, which is the same as ei pi over 2. Likewise, we can show that minus 1 is equals to e to the power of I pi, and negative I is equals to e to the power of I multiplied by negative pi over 2. Although the basic form of complex numbers, the x plus yi form, is better for addition or subtraction between complex numbers, we can also add or subtract complex numbers in the Euler form. This is on the condition that they have the same modulus. So for e to the power of I theta plus e to the power of negative I theta, we can show that they are going to be equals to 2 cosine theta by simply rewriting them in the polar form. So ei theta plus e negative I theta can be written as cosine theta plus I sine theta for the first Euler term plus cosine theta minus I sine theta for the second Euler term. The sine terms will cancel out nicely for us, and thus we are left with 2 cosine theta. Likewise, e to the power of I theta minus e to the power of negative I theta can be shown to be equals to 2I sine theta. If we have e to the power of I theta plus 1, it can be shown that it is equals to this expression over here. And for this, we have to do a little trick for the derivation. So instead of memorizing this formula over here, we will rather perform the trick in order to derive this term out ourselves. So what we can do is to first factorize out half of the argument. So for e to the power of I theta plus 1, it is the same as e to the power of I theta over 2 multiplied by e to the power of I theta over 2 plus e to the power of negative I theta over 2. And thereafter, we see that this term is the same as our first identity. Therefore, we can change this into 2 cosine theta over 2, and this expression finally becomes 2 cosine theta over 2 multiplied by ei theta over 2. Using a similar approach, we can also show that e to the power of I theta minus 1 is equals to 2I sine theta over 2 multiplied by e to the power of I theta over 2. In example 3, we are asked to find out the 3 roots of the cubic equation z cubed equals to 1. So we know that for z cubed equals to 1, there is only one real root, that is z equals to 1, and the other 2 roots must therefore be complex roots. How we can find this is very easily by writing 1 as e to the power of I times 0. Subsequently, we know that this is the same as e to the power of I 0 plus 2k pi. or this is simply e to the power of I 2k pi. Therefore, z is going to be equal to e to the power of I 2k over 3 times pi, and k will be equal to 0, plus minus 1, plus minus 2, and so on. But we just need to pick the appropriate number of roots to represent all the roots. And in this case, we need 3 of them, and they will come from 0 and plus minus 1. And therefore, we have e to the power of I 0 when we substitute k equal to 0, e to the power of I times 2 pi over 3 when we substitute k equals to 1, and e to the power of I negative 2 pi over 3 when we substitute k equals to minus 1 in. Of course, for this first root over here, we can simplify it into 1, and the other two we will leave it as the Euler form. In example 4, we need to express this expression over here as a complex number in the form of REI theta. So this is actually in the form of x plus yi, where x is this and yi is this. So the first thing to do is to change our cosine term and sine term into the Euler form, which gives us z equals to 2 plus 2ei negative pi over 3. Let's factorize out the 2, and we'll get 1 plus ei negative pi over 3. And notice that this form over here is very similar to what we have done earlier in taking out half of the angle before we can substitute the identity in. So I'm going to factorize out half of this angle here. So 2ei negative pi over 6. And what I'm left with will be e to the power of I pi over 6 plus e to the power of I negative pi over 6. And for the term within the bracket, this is our identity, which is the same as 2 cosine pi over 6. And we can simplify it further because cosine pi over 6 is a special angle, which gives us 2 times square root of 3 over 2, which becomes square root 3. Therefore, this expression for z can be simplified into 2 square root 3 e to the power of I negative pi over 6